This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on improper integrals. The first example is the integral from 1 to infinity of 1 over x squared dx. What makes this improper is the fact that it is going to infinity. Our interval is infinite, from 1 to infinity. We are looking for the area under the curve of 1 over x squared on that interval. So starting at 1, going to infinity, what is the total area under the curve? Now it may seem strange that we would measure something over an infinite width, but we want to find that area. But you'll notice how this is going down so quickly. The question is whether or not this area under the curve is a stable number or whether it grows to infinity. So here's how we're going to answer that question. We have the integral from 1 to infinity of 1 over x squared dx, and the fundamental theorem of calculus holds because this function is continuous on the interval from 1 to infinity. If I would plug 0 in, you'd notice there's a problem because we can't divide by 0. But we're away from 0, so the fundamental theorem of calculus holds. But to use that, we have to have an interval from one number to another number. Infinity is not a number. So what we do is we take the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. So now we can actually appeal to the fundamental theorem of calculus, take the antiderivative, evaluate it at b and at 1, subtract, and then take the limit as b goes to infinity. Rewriting 1 over x squared is x to the negative 2. And then, of course, increasing the exponent by 1, negative 2 plus 1, x to the negative 1 over negative 1, as x goes from 1 to b. We can pull this negative 1 out in front. So negative 1, limit b goes to infinity, x to the negative 1, as x goes from 1 to b. So plugging in b for x, b to the negative 1 minus 1 to the negative 1. b to the negative 1 means 1 over b. 1 to the negative 1 means 1 over 1, or 1. Now as b goes to infinity, what happens here? 1 over a very large number, 1 over a million, 1 over a billion, 1 over a trillion. One chance in a trillion is basically 0. So as b gets large, 1 over b gets closer and closer to 0. So this limit is 0, that limit is 1. We get negative 1 times 0 minus 1, negative 1 times negative 1, or positive 1. And let's go back to this picture. So the total area under this curve is positive 1. Now we can only see a little bit of it. This looks like it's pretty close to a half, and this might be around a quarter. So you can see there's not very much beyond that if the total area under that curve is 1. And remember, this interval goes all the way to infinity. I'm just showing it to 8, but it actually goes all the way to infinity. And the total area under that curve from 1 to infinity is 1. Our next example is the integral from 1 to infinity of 1 over x dx. This is improper again because we have infinity here. And let's look at this picture. 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, 1 over 4 is a quarter. We want the total area under the curve for this function, f of x equals 1 over x, starting at 1. You'll notice that the red line is not going down nearly as fast as it did for our last example. So if I add up all of this area, does it hit on a stable number or does it grow to infinity? That's in essence our question. The fundamental theorem of calculus applies here because the function is continuous on the interval from 1 to infinity. As long as I stay away from 0, the function is continuous. But I need to evaluate that at two endpoints. Infinity is not acceptable as an endpoint for the fundamental theorem of calculus. So we'll go ahead and rewrite that as the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Well, the integral of 1 over x is the natural log of the absolute value of x. So we have the limit as b goes to infinity, natural log absolute x, as x goes from 1 to b. Plugging in b, natural log b, minus plugging in 1, natural log 1. Absolute value not needed because b is approaching positive infinity, b is a positive number, absolute 1 is 1. Now, log 1 is 0, fine. But as b gets large, what happens to natural log b? Natural log a million, a billion, a trillion. It gets large very, very slowly, but it does get large. This does not stabilize. This continues growing as b grows. Again, log 1 is 0, so we just have the limit as b goes to infinity of log b, which never stabilizes. That diverges. So the area under that curve is infinite in S. Area under the curve from 1 to infinity diverges. Keeps growing and growing and growing and growing, never stabilizes, essentially goes to infinity. Our next improper integral is the integral from 0 to 4 of 1 over x minus 2. You may be tempted to take the antiderivative, which is natural log absolute x minus 2, evaluate it at the endpoints and subtract, but that's not fair because the function is not continuous at 2. If we plug 2 in for x, we have a division by 0 situation. It is not continuous at 2. That's why this is an improper integral. Looking at the graph from 0 to 4, 1, 2, 3, 4, thereabouts, I guess. From 0 to 4, what's the area under the curve? Well, this part would be positive, this part would be negative. It kind of feels like they would balance each other out on some level. But we need to formalize this. This is an improper integral because, again, the function is not continuous at 2. We're integrating it from 0 to 4. So how do we answer that question? Here's our formal statement. The fundamental theorem of calculus does not apply because the function is not continuous at x equals 2. So we've got to break this up into two integrals. We're going to go from 0 to 2 and then from 2 to 4, stopping at that discontinuity. But we can't plug 2 into the antiderivative here. We're going to have to use some sort of limit argument. Same thing with the second integral. We can't plug 2 in the antiderivative there because it's not in the domain of the function. So we will take the limit as a approaches 2 from the left. We're starting at 0. We're going to 2. 0 to 1.9, 1.99, 1.999, approaching 2 from the left. On this side, we're going from 2 to 4, but we're starting just a little bit beyond 2, 2.1, 2.01, 2.001. So we're taking the limit as b approaches 2 from the right of the integral from b to 4, 1 over x minus 2. Limit as a approaches 2 from the left of the integral from 0 to a of 1 over x minus 2. Now here's the thing. I have two integrals. I don't have to do them both. If one of them diverges, then this original integral diverges. So I'm going to focus on one of them at a time, and as soon as I find one of these integrals diverges, then I can say the original diverges too. So I'm looking at this one. Limit is a goes to 2 from the left of the integral from 0 to a of 1 over x minus 2. The antiderivative of 1 over x minus 2 is natural log absolute value x minus 2 evaluated from 0 to a. Plugging in a, natural log a minus 2, plugging in 0, natural log 0 minus 2. We are approaching 2 from the left, so it's 1.9, 1.99, 1.999. 1.999 minus 2 is a negative number. When I hit it with an absolute value, it becomes a positive number. 0 minus 2 is negative 2. Absolute value of negative 2 is 2. So the absolute value of a minus 2 would be 2 minus a. 2 minus 1.9, 2 minus 1.99, 2 minus 1.999, minus log 2. But a is approaching, again, 2 from the left. So 2 minus 1.9999999 is a very, very small positive number. And there should be a log there. Let's go ahead and put that in. So again, natural log of 2 minus a is a natural log of a small positive number that's going to negative infinity. So this limit does not exist. So this integral diverges. This limit of this integral does not exist. So remember, we started with two integrals in the first part. We wrote it this way, and this integral doesn't exist. We did the limit and showed that that limit diverges. So if that's the case, if either of these integrals diverge, then the original integral diverges. I don't care about this second integral. My conclusion is that the original question also diverges. Our next example, integral from negative 8 to 8 of 1 over x to the 2/3 power. Well, what can we do with this? We recognize that 0 is a problem. If I plug 0 into this function, I get 1 over 0 to the 2/3, 1 over 0, not acceptable. So we have an internal discontinuity, so I'm going to write this as the integral from -8 to 0 plus the integral from 0 to 8, because of the fact that that function is not continuous there at x equals 0. So -8 to 0 plus 0 to 8. But I need a limit here. I need a limit as we approach 0 from the left here. I will need a limit as we approach 0 from the right for the second one. So here a will approach 0 from the left. Here b will approach 0 from the right. At this point, I'm able to go ahead and evaluate the antiderivatives, rewriting 1 over x to the 2/3 as x to the -2/3 in both cases. So to do the integral of x to the -2/3, kick up the exponent by 1. -2/3 plus 1 is +1/3. So this will be x to the 1/3 over 1/3 as we go from -8 to a. Similarly, x to the 1/3 over 1/3 as we go from b to 8, which is what we will need, which is what we have here. Now x to the 1/3 is really cube root of x. Divided by 1/3 is the same as multiplying by 3. So we can think of this as the limit as a goes to 0 from the left of 3 times the cube root of x, as x is ranging from -8 to a. Over on this side, the limit as b goes to 0 from the right of 3 times the cube root of x, as x goes from b to 8. This will be 3 cube root a minus 3 cube root -8. This will be 3 cube root 8 minus 3 cube root b. As a is approaching 0 from the left, -0.1, -0.01, -0.001, we can take cube roots of negative numbers, not square roots, but cube roots are okay. Cube roots of numbers approaching 0 will be approaching 0. Similarly, on this side, if we're approaching 0 on the right, 0.1, 0.01, 0.001, cube roots of numbers approaching 0 will be approaching 0. Now the cube root of -8 will be -2, and the cube root of 8 is +2, so where does that leave us? 3 times 0 minus -2 in this piece, plus on the right side we have again a limit. That becomes 2 minus 0, so that limit really is unnecessary. So we've taken that limit, 3 times 2 minus 0, so 3 times +2 here, 3 times +2 there. That, of course, is just 6 plus 6, and our answer to that is 12. Our next example will be the following. Integral from -infinity to infinity of x cubed. So this is an improper integral because I have infinities on both ends. When that happens, I've got to pick a number in the middle to sort of make that work. So we're going to wind up breaking this thing up. But first, let's take a look at the picture. What does that look like? -infinity to infinity, the area under this piece and above that piece, it sort of looks like they should balance out. You might argue that this should be 0, but it isn't. In fact, if you go -2 to 2, it would be 0. -3 to 3 would be 0. -100 to 100 would be 0. But this integral is not 0 in terms of how we define this. So we're going to take the integral from -infinity to 0 of x cubed dx, plus the integral from 0 to infinity of x cubed dx. Now we have an improper integral here and an improper integral here. Limit as a goes to -infinity plus limit as b goes to +infinity. The antiderivative of x cubed is x to the 4th over 4, so each of those works out the way we want it to it. And again, our same rule occurs. If either of these integrals diverges, then the integral diverges. Let's focus on the second one where things are approaching +infinity. So again, integral of x to the 3rd is x to the 4th over 4. So b to the 4th over 4 minus 0 to the 4th over 4 as b approaches infinity. This, of course, goes to 0. This gets increasingly large. So b to the 4th over 4 will go to infinity as b goes to infinity. That diverges. Remember what we said? We said if either of those two integrals diverges, then the whole thing diverges. Therefore, the integral from -infinity to infinity of x cubed diverges. But that shouldn't really surprise us. We looked at the integral from 0 to infinity of x cubed. What does that look like? 0 to infinity of x cubed total area under the curve? Of course that's infinite. So that integral diverges. And that will conclude this lesson.